Welcome. So today we'll be talking about the first half of section 8.3 on infinite series in your textbook. So we have just finished up discussing geometric series. And so now we're going to be continuing that discussion by considering more general kinds of series. So I just wanted to first start out here by listing a few different series for you to take a look at. And I have the first one I have listed here. This is the geometric series. And so very often when we think about series, we use summation notation, as you've seen, as a compact way of writing a series. But of course, a series is just an infinite sum of terms. So here, again, we're using the summation notation. So we're starting, our indexing variable is going to be k here. And of course, that can change. It doesn't change what your series is, whether you have an indexing value of, say, k or n. You can use anything there, but the k has to match whatever part of the term is going to be incrementing. So here we're starting at 0. So our first term is going to be a times r to the 0 plus a times r to the 1 plus a times r squared plus, and then we're just going to continue on. And here our upper limit, if there was a number up here in the above the summation sign, then we would stop. Since there's not, we just continue on forever. So that's just a little bit of review with our geometric series here. We analyze these quite a lot, and I'll point out here that with our geometric series we did start at 0. And then we continued. Now, most of the series that we'll be encountering from here on out, you do have a few examples in your book that start at 0, but very often they actually start at 1. It actually doesn't matter. You can start at any number and you still have a series. So you'll see an example later on today where I've got the series starting at indexing variable 2. And there's a specific reason for that. So I've listed here a couple of famous, they're not all famous, but just these are some series that we'll be investigating more as throughout the class today. So this first one here, or the second one after the geometric series, is the harmonic series. And it's a very famous series. It has some special properties that are kind of surprising, and so we'll be seeing a lot about this series today. And this is the series, it's just 1 over k as k goes from 1 to infinity, so it's 1 plus 1/2 plus 1/3 and so on. And these other series don't really have a name, but I think it's a good skill to be able to just expand these series out. So you should pause your video right now and write out the first few terms of each of these, and then restart it, and you can compare what you get as I write them down. Okay, go ahead and pause your video now. Okay, and so I'm just going to go ahead and write this down here. 1 plus 1/4 plus 1/9 plus 1/16 plus ... Okay, and this next one we have 1/2 plus 2/3 plus 3/4 plus 4/5. And this last one, when k equals 1, minus 1 to the k is -1. So this is -1 plus 1 minus 1 plus 1 minus and ... Okay, so now we've written these up. I think that at this point now, it's important to ask the question, what do we mean by writing down an infinite sum? So how do we think about infinite sums? And just as we did with geometric series, we approximate them by finite sums. So that leads me to up here, the third bullet point here, that the nth partial sum of a series. Okay, and so if you recall, with a geometric series, we considered the sum of the first n terms, and then we were able to compute so we called, so let me go ahead and just write it down here. We said that Sn is equal to, for the geometric series, Sn is equal to A plus AR plus dot 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 plus A R to the n minus 1, and this is the sum of first n terms. Okay, so more generally, sorry about that, more generally, the sum of the first n terms of a series, and I guess I will go ahead and let me see what your book is using as a, I guess I'm going to go ahead and use a different letter because I've got A's sitting up here with the geometric series. So I'm going to go ahead and say the first n terms of a series sum k equals 1 to infinity, and I'm just going to call, we'll call it b sub k. So the sum of the first n terms is, and we'll call this Sn, and this is equal to the finite sum. And so this would be the sum from 1 to n of bk, right? And this will be equal to b sub 1 plus b sub 2 plus dot 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 all the way up to b sub n. Okay, and what we want to do is we want to think about what happens as n gets large. Okay, so Sn is the nth partial sum of the series sum k equals 1 to infinity b sub k. Notice here that things are a little bit different because in your geometric series we started indexing at 0. So in this case, over here, I'm just going to go ahead and switch colors here just to show you the difference. This is equal to the sum from k equals 0 to n minus 1 of a r to the k, right? And so here you see that there's still n terms in the sum Sn, but the indexing is just shifted by 1 because Sn is starting, or sorry, not Sn, but because the series here is starting with indexing variables equal to 0. Okay, so there we have the partial sums. So what I want to point out here is, in fact, that the partial sums are a sequence themselves. So let me go ahead and just do that. Note so every series has okay, so there it is. So let's go ahead and go up to the series that you have here. Now we already wrote down the partial sums of the geometric series. So what I would like for you to do is, I'm going to do one of them here. So I'll just switch colors. We'll just do it in purple. So partial sums of this series are, and actually let me back up a second. So the first there's actually two associated series here. There's a series of partial sums, and there's also the series of terms. And what I mean by the series of terms, I put up here summands, right? And so the summands are just the individual numbers that we're adding together. And so the sequence of terms is just the numbers that we're adding up here. So 1/1/2. It's a list. So you want to be thinking about this as an infinite list of numbers, 1/1/2, 1/3, and so on. ... So this is a sequence, not a series, but it's certainly related to the harmonic series. And then we have the sequence of partial sums. Okay, and that's what we just defined here. So, so if I say the first item in the sequence of partial sums is just the sum of the first term, so it's just 1. Then the second item in the sequence of partial sums is going to be the sum of the first 2 terms. So it's going to be 3 halves. The next in the list is going to be 1 plus 1/2 plus 1/3. So that's 3 halves plus 1/3. I think it would be, let's see, 11/6 if I'm not mistaken, and so on. So to get each successive partial sum, you take the previous partial sum and then you add the next term to it. Okay, so what I would like for you to do is go and actually write this out for each of the next 3 series. And then I'm going to go ahead and stop this video here so these don't get too long. And when we pick up the next video, I'll just give you the responses that you should have written down there, and we'll continue our discussion.